All right. Well, thank you for having me for this second talk. This is joint with my co-author Weiji, who is also at Stanford GSB. Normally in economics, I try not to present published papers or even papers at the late R&R stage, because whatever you tell me about this paper, I won't be able to do anything about. So if you have suggestions for how it could be better, maybe rephrase those as suggestions for the next paper. So I want to think about online platforms. I think what I have to say is relevant for news feeds and stuff like that, but probably the closest fit for my assumptions is something more like Facebook Marketplace. So I want you to imagine you're looking at this list of things you could buy. Perhaps one of them is an advertisement. The others are like things that are being sold by merchants. There's a few things going on here. The first is that this format is only capable of displaying 6 things to you on the phone, because you want to be able to look at them and read a little bit about them, and there's a limited real estate. So just like we were talking in the last talk with YouTube, they can't show you a list of all the videos on YouTube and have you pick one. The list is simply too long. So there needs to be some kind of selection. And so I'll call that content. And as I said last time, the thing that comes most naturally to me is to think about you as enjoying this content for an instrumental value. Maybe you're choosing which one of these objects to buy. If it's a recreational value, you're watching videos on YouTube because you like it, because it's fun. That mostly fits into the framework as long as it has the sort of more is better property that we talked about last time. So you're receiving this content, and the key sort of question that you as the user face is when to stop, right? So stop could mean stop and buy one of these things. Stop could also mean stop and just use a different app, right? So those would be 2 examples of actions, right? One is you bought something, one is that you use the app. And that's the user's choice. The algorithm is deciding from this pool of potential things to show you what it should put in the top 6. And that's controlled by what I'll call the platform. So in this case, it would be Facebook Marketplace or YouTube or what have you. And the goal of the platform is to have those advertisements in there. Now,
or clicks.
Sorry?
Impressions or clicks.
Good. So I'm going to talk to you about 2 different models. One where the advertiser profits basically from just having the thing there, and the other where the advertiser needs you to click on it. Now, the model is an abstract theory model. It doesn't have either clicks or ads, so those are my interpretations. But we don't know which one of those things is the right thing to think about. And so we tried to cover our bases and think about both things. The algorithm is thinking about quality here of the content. But the reason it's thinking about the quality is that it wants the user to not stop, right? Because the more the user continues, the more of those ads it gets to show. Presumably, the more likely the user is to click on
them. I mean, just from their incentive, do you care about the quality of the marginal thing they're showing as opposed to?
Sorry?
I'm just trying to think out loud here, but I think what they care about is if they want to maximize the duration of engagement, is they care about the quality of the marginal page they show them.
Yeah, so when you swipe up, they have a decision to make, and they need to show you something that will get you to look at more ads instead of stop.
So they have also incentive for it to spread out quality as opposed to
Good. So the question is the next thing they show you going to be the best thing they have or not? Right? And that's the kind of question we want to be able to answer. There's an information bottleneck here, which is that even if they did want to show you the best 50 items that they think might be a match for what you want, they can't do that. They can only show you 6. And that's what I'm going to model in the sort of rational inattention stuff, is that information bottleneck. So the incentives here are a bit misaligned, right? The user wants to just find the best thing. The platform doesn't necessarily want to show them the best thing right away. That might not be the right way to maximize the ad revenue. And that's the tension that we're going to explore.
But you don't have I guess we heard yesterday about system 1, system 2 type tension, right? Where maybe the user cares about their like rationally chosen optimal thing as opposed to like.
Yeah, so I am, it's an interesting question, actually. I was about to say I'm not a behavioral economist, but that's really just because behavioral economists don't think this rational inattention stuff is behavioral, even though it obviously is. I'm not really sure why we use that language. But yeah, my user is going to correctly anticipate how this platform works. And the platform is going to know that. And so it's not going to be a situation like where the user is conflicted within themselves, but we will focus on the conflict in the platform.
But it's all in the system too broad.
Yeah. Okay, so
can I just understand this putative platform is all about sales. It's not content, and it's some of them are sponsored. The whole thing is sales. It's not other content.
No, the assumption here is that say Facebook Marketplace or whatever does not care if you buy one of these things and which one you buy, unless you click on an ad, which they would profit. But they don't actually care about what decision you make. And that's the way in which I think it is like YouTube doesn't care what video you watch, provided that you watch their ads as well.
The user is what is.
The user cares.
It's not, but is the user not liking ads? Are they an active element? Or?
So good. So the question is going to be, okay, so there's a sense in which I might just viscerally dislike seeing this ad. That's not in the model. But the user is going to dislike this ad because it is taking up one of the 6 spaces here, right? And so there's a sense in which the more that the platform is sending you, that the platform wants you to attend to, that you do not want to attend to, the more you might dislike the situation. So I will think about these content as signals about an unknown state. So remember last time I gave you the example X, the unknown state, is a list of cars with prices and qualities and characteristics. This is what I had in mind. The ad impressions, I'm going to say there's some measure of attention, and that's going to translate into revenue for the platform. There's an opportunity cost of time for the user. So the user does not like using this platform so much that if they already knew which thing they wanted, they would continue to do it anyways, right? So the user is thinking about stopping. There's an information bottleneck, which is the rational inattention thing I showed you last time. And then the algorithm is going to design a sequence of signals that it sends to the user. So
on the user preference side, so if it's not for instrumental reasons, but the intrinsic value of information, how do I think about that relative to the cost of time, which is almost the same thing, right?
Good. So remember that because X is finite, there's a limited set of things that one can learn from using the platform. And even if the user just loves learning, they also love time.
So I guess in that formalism, you have kind of decreasing returns built in.
Exactly. And you'll actually see there's going to be an assumption, which essentially bakes in that you won't learn everything and take forever. Good. Okay. So now that's the setup. What do we find in our setup? First, we find something about the nature of content, which is that the content should not cause you to update your beliefs a little bit. It should either cause you to update your beliefs not at all or in a big jump. And the way we interpret this is that the platform, rather than offering you sort of a wide range of shallow content, should offer you a rabbit hole on one particular topic. And you may go down that rabbit hole, in which case fantastic for the platform. It's going to take a while. Or you may not, in which case they will try a different rabbit hole. But that's the plan for the platform. And so in that sense, the content is deep and narrow. The comparison here is between what the user would choose if the user were designing the algorithm for herself. And the user would choose something that was a little bit broader and less deep in terms of the content. So that's
okay, just define depth and narrowness.
Yeah, so depth is going to measure the amount of information you acquire in the event that this thing was the thing you were looking for. Narrowness is going to measure the likelihood that this thing is the thing that you were looking for. So what I'm going to send you is something that is a lot of information. It might not be the information you want with fairly high probability, but if it is the information you want, it will be even more information than you wanted.
Kind of hiding Easter eggs.
Exactly. There's going to be zero consumer surplus here. The platform is going to extract all of the surplus. And to me, that's a little bit surprising because the user can decide whenever they want to stop. And they have surplus from this information. And so I thought that the user would end up with some surplus and the platform would end up with some surplus. And that turned out to be wrong. The platform gets all the surplus here. And it takes longer than the user would like. The user is going to spend more time on the platform than they would if the user could design the algorithm. What is the platform going to do? It's going to give you two kinds of signals, what we will call suspensive signals and decisive signals. Suspensive signals induce more browsing. They make you more uncertain in a particular way, which I will mathematically describe, that raises the value of additional information the platform can send you.
How would more information make you more uncertain?
Well, remember, I'm sending you a signal and you have an initial prior. And let's just think about a line for a second. There's a point in the middle of that line where you are maximally uncertain. I'm going to send you a signal which is either going to move you all the way to the endpoint or back toward the middle. The all the way to the endpoint one is what we're calling a decisive signal. That means it's a signal that's so informative that it causes you to decide. You're stopping, you're doing an action. But if we're not stopping and doing an action, I want to raise the value for you of continuing to scroll, right? And so I'm going to try to send you signals that sort of raise the value of my future signals to get you to keep going. Yeah.
What actions is the user taking? So they're paying attention and
So
whether to scroll.
Good. So there's, do I stop or do I not stop? And then after I stop, what do I do? Right. So it's the exact same model we talked about yesterday. You can either stop at any point and decide to do something, or you can continue.
But there's a sequential search aspect about it.
There's a sequential information aspect about it, yes.
Okay, but there's a recall, so I can scroll, and then end up buying the first.
There's only a fixed set of actions you can do,
Got it.
and you're just updating your beliefs about the values of those different actions.
Because the items don't necessarily correspond to your actions.
Yeah, I mean, I would say you can scroll back up and pick one from
Right.
Sorry,
Oh.
in terms of the, maybe we already discussed this, but in terms of the advertising, it sounds like you're describing display advertising, so cost per impression rather than cost per click type of.
Well, I wanna, you're gonna see there's sort of a thing in the model.
Yeah.
And I claim that in two different cases of this abstract thing, it captures both of those possibilities. And I will talk a little bit about how they're different.
Yeah.
And they are different.
Because the incentives for the platform seem quite different.
Exactly. And that's gonna manifest in different outcomes. Yeah, excellent point. Okay, good. So what literature is this building on? You learned about all this yesterday. The user optimal benchmark, which is where you can think of this as the platform is benevolently designed to maximize user welfare. You can think about it as the user chooses her own information, however you want to call it. That's dynamic rational inattention models. Weiji and I have separately worked on those. There's an information bottleneck here. That's just the rational inattention literature. And then there's a new thing, and I didn't really talk about these papers yesterday, which is about sort of parceling out information over time to keep someone coming back. And so there's an existing literature on that topic. I'm not really going to talk too much about these papers, but I will just say that they are probably the closest non-rational attention cousins.
This is sort of like the suspense and surprise stuff.
Yeah, exactly. Although that's a little different because that's an explicit situation in which more information is not better. That's the suspense part, right? So that's working on the preferences. We're not going to be doing that. Okay, so there's this state, X and X. There's a prior belief, Q0. And now there's a stochastic process for beliefs, QT. So this should remind you of yesterday. And that's what options are there. There's a stopping utility that you get. This is the indirect utility, right? So if I stop with this belief and then I choose the best of my options, or perhaps take an outside option, this is how much utility I'll get. And so what the agent is going to do is choose a stopping time to maximize her expected utility, less the cost of delay. Oh, there's a straight parenthesis there. So this kappa is like the opportunity cost of time. The add impressions, there's going to be this kind of flow revenue. Oh, there's another typo here. This should say G, not H. That will be important in a second. Where there's some information measure and the flow of ad revenue is proportional to the increase in that information measure. There's an information bottleneck, which is how much information can be processed. The reason I said this should say G is that this one says H. The bottleneck, which measures how much the agent can learn, does not need to be the same thing as what the platform benefits from in terms of revenue. So one is measuring the information associated with the platform's revenue. The other is measuring the information.
This is now like the Sims penalty for attention.
This one is like the Sims penalty for attention. This one is not, right? It's like the value of information, but it's the value of information the platform places on the user. And so what the algorithm is going to do, remember this one should say G, is that it's going to maximize the total amount of information acquired by the user about the advertisement. So that's the per impression or per click idea, subject to the incentive compatibility constraint, which is that the user decides when to stop, and the information bottleneck. And that's the problem.
So that you model the ad itself also as a source of information.
The which itself?
The ad itself is also kind of a signal.
Yes. So the question is going to be, are these ads also products that I'm looking for? Or are they unrelated ads that are not related to the products that I'm looking for? And that's going to actually create a bit of a sharp separation between two cases of the model. Yeah.
So is it correct to think about a flow of items basically, and the user endogenously chooses with what intensity they're paying attention to them? Some of them will be ads, some will not.
I think that's right. Morally,
Right.
I mean, it's a continuous time model. The information notion is abstract. Like,
Sure.
I like that interpretation. I can't quite say that that is exactly
Yeah,
what's captured by the mathematics.
Spiritually,
That's what I'm aiming for. Yeah.
But formally you get signals, you're not getting items necessarily.
Well, as we discussed yesterday, what we're going to do is we're going to think about this QT as a martingale. And the algorithm is going to choose any process QT subject to it being a martingale. That's that Bayes plausibility thing we talked about yesterday. In the background, there are signals, but I'm not going to think about what they are.
But that also, so that does mean that you cannot really scroll back. You can scroll back to choose, but not to learn more, right? So you have the sushi conveyor.
Yeah, I mean, there's an assumption here about memory, which is a little subtle. So when you say beliefs are martingales, you do slip in the fact that you don't forget.
Right.
Because if you forget, actually, your beliefs are not martingales and drift back towards whatever belief you would have after having forgotten everything. So there is a memory aspect here.
But is it dynamically consistent, or might I ever want to go back?
This problem is dynamically consistent. A question, which you can ask and we will attempt to answer, is if the platform offers some belief process Q and it starts, and then we say, would the platform continue to offer that belief process Q from this spot? Or does the platform need commitment? Right, remember one of the things we talked about yesterday was the importance of commitment in Bayesian persuasion models. This is not exactly Bayesian persuasion, because the platform doesn't care what action is hiding inside here. The platform is not trying to get the user to do any particular action. So maybe you don't need commitment. Maybe you do. We'll find.
The story is something like platform commits to hide information on screen 3 and therefore incentivizes the user to go to screen 2.
Yeah, I mean, definitely they're not going to show all the best information they have.
But then once there's screen 2, you can say, oh, I'm going to show you screen 4 now.
Yeah, so the problem is if the user starts to think that it's always 2 screens ahead, then they're just going to give up. So that's not going to be an equilibrium either. Right? Yeah, so we'll see. Okay, I want to give you a little example. This is like a toy example, which helps think through things. So there's an unknown state, let's call it left or right, L or R. And then there's a signal, and the signal, you could get either SL or SR, and SL is more likely in the L state, and SR is more likely in the R state. So I'm assuming here that alpha is bigger than half. And so I'm going to think about alpha as being related to the breadth of the signal. And I'm going to think about P as being related to the depth of the signal. And so the way I've parameterized this signal structure, alpha is the rate at which this signal will arrive. Now, notice that neither of these signals might arrive in any particular instant, right? So alpha is the rate at which I learn anything. And when I get a P, if P is really high, I learn a ton. If P is like slightly more than a half, then I barely learn anything from each signal. And so different combinations of alpha and P will have different kind of learning dynamics here, right? If alpha is very high, I will learn quite frequently. But if P is low, I won't learn much each time. And in fact, if you sort of really painfully dig into it, you can think of the alpha to infinity, P to 1/2 limit as a Brownian motion. On the other hand, if P is 1 and alpha is quite rare, then the moment I get a signal, I know exactly what the state is. But I might not get that signal very often. And so the information bottleneck, if we just use Sims's mutual information as an example here, is basically alpha times some increasing function of P minus 1/2 is less than 1. So there's an alpha versus P trade-off. I can send you broad signals that are likely to update you about something, but don't convey a lot of information about any particular topic. Or I can send you narrow signals that convey a ton of information, but are unlikely to be useful. So I view this as like a breadth versus depth trade-off, is what is captured in this mutual information cost here. And so the user's decision problem is to choose an action, L or R, little l or little r. And the game here is just that if my action is little l and the state is big L, or my action is little r and the state is big R, I get a utility of 1. Otherwise, I get a utility of -1. And I have a cost that is paid per unit time. So I want to wrap things up. So that's the simple example. And so these are the primitives.
I'm just trying to understand the formalism example. So basically, I can think of the alpha as like what's the probability that it gets signal at all, and then the P is how distinctive that signal is.
Exactly.
Discrete time periods.
Yes.
But I guess I only observe the end result, right? So I don't. It's not as if the alpha draw gives me a 0. I don't really know if that's what happened.
Well, yeah. If you don't get a signal in this instant, then your beliefs just remain at what they were, and that's because the alpha is like a symmetric in a way. So the user is gonna, if the user were choosing the alpha and P, would say, well, if I get a P that's high and I stop and make a good decision, that's beneficial for me. I want to learn a lot. But if I have a low alpha, it's going to take a long time. So high P, low alpha is a strategy where I make good decisions, but it takes a long time. Low P, high alpha is a strategy where I make bad decisions, but it doesn't take as long. And I have this trade-off. And so it turns out that the optimum here is that P is E over 1 plus E. That just has something to do with logs and Shannon entropy. And alpha is whatever number it needs to be to satisfy the constraint given this P. So that's the user's optimum. But the platform can do a little better. So suppose the platform wants this whole thing to take a little longer.
What's the stopping rule for that P and alpha?
It's that you stop after the first signal, SL or SR. A better strategy for the platform would be to say, you know what, I'm going to make your P even bigger. I'm going to do 4E over 1 plus 4E. So this is saying, I'm going to give you way more information when this signal arrives, but I'm going to slow down the arrival. And if you take these two parameters and you plug them into the user's objective function, you will see that it is still positive. So even though this is not what the user would want to choose for herself, it's still better than stopping and making a decision right away. So the platform's problem is actually to solve, I want to maximize the amount of information the user acquires, which is equivalent in this case to the amount of time, subject to this constraint, which is that the user has to be willing to play along. The user can't decide to opt out. And you run through this. You get a solution. The solution has 3 properties. The first is that it is analogous to a static rational inattention problem, even though this one had dynamics and Poisson signals. And the platform is going to choose a P that is bigger. And what that means in the space of posteriors is that the posteriors are spread out, they're wider. The user is going to end up acquiring more information using the platform than the user would have chosen to do for herself. So that's what we call extreme beliefs. I want to be very careful. the referees called us out on this one. Extreme means something in math, and it means something colloquially when we talk about platforms like YouTube. And we are saying the math one, not the YouTube one. So this just means more spread out. I obviously want to sneak in, and I think it means the YouTube one, but that's probably over-interpreting things. Zero surplus to the user. So the platform, when they solve this problem, they have this constraint. The user has to be willing to play along. They will drive the user to this constraint. The user will be no better off than if they did not use the platform.
So extreme beliefs here really kind of beats knowledge, right?
Yeah, so good. So in the paper, we talk about internet platforms and stuff like that, but we have also a different context, which is a teacher teaching a student. And in that context, extreme beliefs would mean the student knows a lot. And that has obviously a more positive spin than YouTube radicalization or whatever. So zero surplus to the user. And then beliefs remain at the prior in this example until you stop or decide. And that's the suspensive signals, they keep you at your prior, or the decisive signals, you immediately decide. And so these properties are not just properties of this example, but actually properties of this entire class of models. And that's kind of the result of the paper. So here's the...
That's risk commitment by the platform.
Well, we'll talk a lot about that. Or actually, maybe not in this talk, but there's a lengthy section of the paper. And I don't want to spoil the surprise, but I will tell you what happens with and without commitment. But right now, with commitment.
Are the signals Poisson by assumption, or do you start with a chunk diffusion process and that method being?
So in that example, they were Poisson by assumption. Now they are martingales. So they don't even need to be jump diffusions. They could be weirder than that. But yeah, they will end up being Poisson, but that will be because that is optimal. So the platform is going to choose a martingale for your belief process and a stopping time to maximize its payoff, which is the G's. Subject to that stopping time needs to be the best thing for you. This is the incentive compatibility requirement. And notice that this sneaks in the tie-breaking rule. Remember we talked last time about how this is saying the principal chooses tau. The agent has to be willing to do tau. But if there's other things the agent is willing to do, the principal gets to pick. So that's embedded in this formulation is the tie-breaking rule. The information bottleneck and Bayes plausibility.
In terms of interpretation, so the G is really platform wants the user to learn a certain thing. The H is that the user doesn't want to learn something else.
The H is that the user is constrained on what they learn. So the H doesn't have to do with preferences. It's a technology. The user can only process 6 things at once. The G is which of those 6 things.
The H we think of as just generic information being costly. The G is something about more specific about the kind of information.
Exactly. Yes.
And the U is another thing that's a specific thing about
the U is what the user wants to learn.
So in a way, the G and the U are kind of symmetric.
Yes, the G is what does the principal want the user to learn. The U is what does the user want to learn. The H is what is the constraint on learning. We're going to make an assumption. This is
it's right. The G could come from some kind of persuasion objective. For instance, I want you to buy this thing. Or
it turns out no, because remember, like in the action that the user chooses is like hiding in here, okay. And so there is a way in which one can try to make this persuasion, but in general, no, I think. It is not the same. And the commitment result features that. The assumption is that you would rather, as the user, learn nothing than learn everything, given the information constraint. And that's basically saying it would take too long to learn everything. So if everything and nothing were the only two things on the menu, you would choose nothing. And this keeps us from having to have a bunch of caveats in our results about like assuming interior beliefs, blah, 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 blah. Right? So it avoids a corner case. All right. So as we've been discussing, H governs the cost of processing information for the user. G governs the benefit to the platform of sending information. And there's two leading cases I want you to think about. One is where G is equal to H. That's where the platform doesn't care what the user learns. They only want to maximize engagement. I interpret this as a setting in which the ads are mixed in with the content in a non-separable way. So if I measure how much content you look at, that's the same as measuring how much money I get. So this is common in some media environments, right? Like, we talked about Nielsen in the context of data, but their original business was measuring how long people watch TV shows. That number translated into what could the TV company get from advertisers for ads, right? So in this interpretation, the platform is essentially paid for the time the user spends on the platform. Now, that's not totally right. And the reason it's not totally right is if the platform sends you no information, the platform does not get paid. So there's no incentive to drag things out here. The platform is getting paid based on the time spent, assuming it is maximizing your information processing at each moment. But if you were to violate that assumption, then the things would not be the same. Okay, so that's case one. That's sort of impressions-based advertising. Case two is that I want to think about the state space as consisting of a product of X1 and X2. And X1 is what the user cares about, and X2 is what the platform wants them to pay attention to, right? So this is the case where like you are looking for cars, the platform is advertising perfume. You don't want to look at the perfume ads, you want to look at the cars. But if they can get you to look at some perfume ads and maybe click on one, then they get something. So here, the platform only gets paid if the user pays attention to the perfume ads.
It's almost like teaching you were trying to.
Yeah, so this is why the other example in our paper is teaching. So this case would be, I want you to learn as much as possible. I don't really care what course material we cover. This case is something like, X1 is what is on the text. X2 is the actual knowledge I want you to acquire. And you only care about the test, but I want you to acquire the knowledge. And I need to kind of provide the right mix so as to keep you paying attention. So if that resonates with any of you in terms of your own teaching, tell me. All right, so there's the platform's problem. How are we going to start this? Because this is kind of a complicated problem. Right, the space of stochastic processes that are martingales is large. The space of stopping times is large. How can we get a handle on this? And the first observation is that for any stochastic process in stopping time, there is a law of the stopping belief, the posteriors, right? A probability measure over posteriors. This is what we talked about yesterday. And I know that if you tell me that this constraint is satisfied, then first off, I know that the stopping beliefs under this distribution on posteriors must be better than stopping immediately, right? The agent had to be willing to go along with it. So this is a kind of a classic trick in economics. You have an IC constraint, which is like really an infinity of constraints. I'm just going to think about one of them and hope that that's the only one that binds. So that's the strategy here. So I'm just thinking about the constraint starting from date 0 and saying the utility that you get less the cost of delay has to be better than stopping right away to get you to use the platform. I also noticed that the time it takes and the cumulative information are related by this constraint. That's just an integration. So everything in this big space of stochastic processes and stopping times satisfies these constraints. And notice here that these expectations are taken with respect to the law of the posteriors, which is a much simpler space. It's just a measure on probability distributions, instead of the much more complicated space of the stochastic processes.
Created a relaxed version of your optimization problem.
Exactly. So the strategy is say, all right, I know that. Let's write down the relaxed problem, solve the relaxed problem, which is actually a pretty simple problem. And then maybe we can implement the dynamic problem using the solution to the relaxed problem. Yeah.
Maybe digressing a bit, but the role of K or whatever that is, the constant of the cost of waiting. Seems to me that the problem doesn't really depend on that, because QT is a Martin gain however you measure time. So however you measure time is arbitrary.
Good. Yes. So that's an excellent point. So like if I change my units from seconds to years, right? That changes this number, but I can undo that change with this number. And then as long as I change this chi number in the same way, then it's the same problem. That's right. So there's a unitless sense. It does matter that it's not 0.
So that was my next thing. If we did set it 0.
Yeah, if we did set it to 0, then my assumption 1, which is that you would rather learn nothing than learn everything, because learning everything takes too long, would never be true, because nothing takes too long, because you have infinite time. So you need it to not be 0.
One is not 0, you want to.
If it was 0, you've still got a well-defined problem.
Yeah, but you're going to end up learning everything.
You want to go as fast as possible once it's not 0, right? Because just accelerate the marketing as much as you can.
Well, okay, so yeah, if this guy were infinity.
Well, like with this guy, like,
okay, let's get rid of that. So let's look at the problem. Get rid of your constraint. Set K to 0.
Yeah.
With a well-defined.
It is still a well-defined problem. And in fact, the papers that I mentioned, the close cousins, are actually doing that and not this. So we think this information bottleneck is interesting in terms of how it interacts with these other things, and that they do play out over time. And that's the aspect of the problem that we're studying. But you're right that you could have gone the other way. And many people in the literature have. So we have this relaxed problem, which is pick a distribution over posteriors, subject to the average of the posterior being the prior, to maximize this expectation of the G, subject to that. But when you slap a Lagrange multiplier on this and just add it into that, you realize it's just a static rational inattention problem. So it has a solution with finite support. And that actually comes from the embedded assumption that there's a finite number of actions. And then when you can do better than 0, that is when you can get the agent to learn anything at all, there exists a multiplier such that you're doing the static rational inattention problem. But the cost of information is a little funky. Ooh, that's a typo. It's minus the H.
So the solution is now over distributions over posterior values, right?
Yes. the cost function now has the normal cost, but it's actually, and again, this should be a plus, the cost is reduced by the principal's benefit. So it's like you're solving a rational inattention problem with a lower cost of information. And so remember, one of the results we're building towards is that the principal gets the agent to acquire more information than the agent would want to. That's because of this equivalence.
You strengthen that too.
Sorry?
You've got this solution with finite, but don't you only need a 3-point support? The reason being cues that Martin has, so I think of the sort of scholar hot type, you know, choose it to be any stop it, we can choose a stopping rule so that Q stops to be any distribution which has got a fixed mean. So then you've got two constraints. One's an inequality on the difference between expectation of a function, which is u of q minus something h of q, maximizing function. So you're in a sort of a 1, 2, 3 dimension surface in 3-dimensional space.
No, remember that these objects could be living in an arbitrarily high dimensional space, right? Like the Q is a vector in Rn for some potentially quite large n, right? And what you're going to do to solve this thing is the standard concavification. I should say there's another typo here, which is that the H is on this one, but the G is on this one. You can tell that these slides were made when we were assuming H was equal to G, and then we realized that H not equal to G was also interesting. So I apologize for the typos. Good. Okay, so we have our relaxed problem, and then the question is, how do we implement it in the dynamic problem? Because when we solve the relaxed problem, we just have a pi, which is a distribution over posteriors. But it turns out there's a pretty easy construction, which is I'm going to keep your belief right at the prior with Poisson signals that have a hazard rate of alpha. You are going to randomly jump to one of the posteriors in the support of pi, and each of which has the appropriate probability of pi. That's what this says. So once I've solved the relaxed problem, I can go back to the original problem and tell you a stochastic process that is the solution to that problem.
But we don't know that the solution is unique, right? It could be building information a bit more continuously.
Excellent. So yes, we know it is a solution. We do not know if it is the only solution. It is not the only solution. But there are some properties that all solutions have in common, and that's what we're going to talk about next. Right? So you're absolutely right.
But anyway, this is kind of the worst thing from the user's perspective, where you get no information. What about it?
Yes. So this is going to keep the user exactly at their outside option, which is exactly where they started. Okay, so combining our propositions, we have either you can't get the user to do anything, you might as well just not send them information. Or you're going to send them information, and this alpha dilution is an optimal strategy. So you get ex ante IR binding. That means full surplus extraction. The user has no benefit from using the platform relative to their outside option. Notice here that I do this, and then because if the signal does not arrive, the user is in exactly the same spot that they started at. I don't need any commitment to do this at all. The optimum just keeps them at this belief. So it's entirely time consistent for the principal to just keep them there. And this is our cue that maybe this is quite different than Bayesian persuasion, right? Because in Bayesian persuasion, commitment is absolutely essential. Whereas here, no, I can get the exact same thing with and without kinetic. It has the Poisson type signals. That's that narrow and deep idea.
Sorry, I guess the stationary flow is exactly what prohibits this. Like in 2 screens, I'm gonna show you this thing.
Yeah, it's always an exponential distribution of screens with, and you know, it's like the bus waiting thing, right? But, and this is what Max had earlier, all I've said is that this is an optima. I haven't said all optima are like this. And so that's kind of what I want to think about next. So I want to characterize policies under any optima, not just the one we just constructed. And to do that, I want to think about the user optimal benchmark. So QU and tau U are what the user would choose if the user were making all the decisions here. Which I think is I mean, we talked in the previous talk about like what is the appropriate counterfactual. I think that's an interesting one. But you know, it's obviously hard to implement in an experiment. But from a theory perspective, I think that's the right
I think it tie things a little bit together, and I think regulatorily would be very interesting to think.
Yeah, like it would be a great objective for Ofcom, right?
Exactly, like giving users some means to control the algorithm in a practically feasible way and setting objectives of the algorithm.
Or even just trying to align incentives so that whoever was designing the algorithm was doing so in the user's best interest, right?
But it seems like it's one simple way is like to say like here's a bunch of different feed algorithms you can pick from, or something like that, right?
Yeah. So we can do the same equivalence trick in the user's problem, and we recover the classic rational inattention problem. But notice that that G is not there. So the user's problem and the principal's problem are very similar, but the principal acts as if information costs less because they have this added incentive to show the acts. So let's let QU be the union of the support of all user optimal pies. What does that mean? Remember, pi is the distribution of posteriors that the user might end up at under some optimal policy. The support is just the set of all those posteriors. The union is saying, well, there are many optimal policies. Let's just add up all the posteriors that there might be and just put them into one big set. Let QP be the union of the support of all platform optimal policies. So same idea. Just take all of the platform optimal policies, look at their supports.
It's all for fixed U and fixed H and fixed G.
Yeah. So we're holding the problem fixed and just comparing user and platform optimal. And the proposition is that these guys are not in the convex hull of these guys. So that's a little hard to visualize. So some diagrams might help. So I want you to imagine a tetrahedron. So there's 4 states. So you have to use your mind. The prior is right in the middle of the tetrahedron. And this is 2 actions. And so one thing that's kind of interesting about these problems is that the number of actions is what determines the dimensionality of the space in which the posterior beliefs lie, not the number of states. So even though there are 4 states, there are 2 actions, and the user is going to want their beliefs to be on a line segment. So these 2 blue dots are the 2 posteriors in this 3-dimensional space with 4 states that the user might want to end up at. So remember, it's the convex hull. So I want to draw a line between these 2 blue dots.
So the user wants noisier information, but more quickly, it's good enough to make a decision.
Yeah. What the platform is going to do is get the user to posteriors that are outside the line segment connecting the blue dots. That's what that convex hull posterior business means. More information. is what we were calling extreme beliefs. Again, probably shouldn't call it extreme in the sense of YouTube radicalization or whatever. It's extreme in the mathematical sense. It's stretched out.
Precise.
But this is the case when H is equal to G. And the strategy when H is equal to G is to give them more of what they want than they want. So the way I like to think about this is with the teaching example. The idea here is you want to teach to the test, but you want to make them work harder than they would want to work on their own to pass the test. So you don't bother to cover the material that's not on the test, but you try to stuff them full of knowledge that is relevant for the test. That's the strategy when H equals G. And the intuition
again is a whole semester and then just teaching everything in the last lecture.
Yeah, I mean,
The formalism material.
the idea here is if I try to get you to learn something that you don't want to know, I'm using up your information budget and I'm taking up your time. So, you know, it's less valuable to you. And I could probably do better by just giving you more of what you do want to learn about. That would relax your participation constraint and let me slow down the process even more. But when G and U are not aligned, so that's what I mean by that perpendicular, remember, is that G is about X2, the U is about X1. Then I have a very different strategy. You see, the user would choose these two blue dots. That's the same. And you started from this prior. But now what the principal is going to do is spread out each of those blue dots into two green dots. They're going to give the user the same information the user would have gotten on her own about the stuff the user wanted to learn about, and extra information that the user did not want to learn about that the principal benefited from showing them. So again, if I think about the convex hull, which is that blue line segment, the green line segments are outside of it, but they're outside in a different way, right? Here, they're outside by providing information the user doesn't want, whereas in the previous example, they were outside by providing more information than the user wants. Now, in the general case, there's going to be some combination of these two things. I don't want you to think this is an either or kind of situation, but it sort of teaches us something about what the strategy is. Should you try to just mix in the ads and the content so that the user sometimes gets something that they don't really want? Or should you just try to give them even more of what they want? Okay. We want to characterize not just the outcomes. That was what I was talking about now, is like, where do beliefs end up? But what is the process that they take to get there over time? And so to do that, I'm going to define this thing called V sub R. The R is restrictive. So this is the value of information to the user in a rational inattention problem. But it's not an arbitrary rational inattention problem. The user is required to end up at one of the posteriors that the principal has chosen. So that's the restriction. So the user is choosing pi prime as in a rational inattention problem, but not over the entire X or P of X. They're choosing from a restricted set of posteriors, which are the posteriors of pi, the ones the principal chose.
And we're now solving the general problem again, or?
No, this is a definition. And I will say that when this thing is equal to or greater than 0, or 2 is more uncertain than the prior. So when the value of information to you is going up, that's what I mean by being more uncertain. That's a little colloquial slippage, but this thing goes up, is our measure of the value of information. And so a belief is decisive if you end up at the stopping point in the principal's problem. And it's suspensive if you are not stopping and the value of information is at least weakly higher than where you started. So the value of information has gone weakly up. In any solution to our dynamic problem, the beliefs will be at one of these 2 points. That is, they will never get to a point where the value of information has gone down, but you are still continuing. That's what's being ruled out here. Either the value of information goes up or we stop. So let's go back to a simple example to kind of understand that. We have a state L or R, prior is Q0, information bottleneck will be Shannon's entropy. User's decision problem is the same as in the earlier example. It's just you want to match the state, and there's a penalty for time. This graph is showing you where beliefs end up in the principles problem and in the agents problem, depending on your prior. So what does this graph show us? If you are over here with your prior, actually the only thing that happens is stop immediately. You already know enough to make your decision. There's no point in learning more information. If you're up here, same business, stop immediately. But if you're in this middle between Q lower bar and Q upper bar, the agent would choose to continue. The principal will get the agent to continue. But the agent would always choose posteriors that are equal to these dashed lines. The principal is going to spread out their posteriors by being on these black tents. So the principal is giving more information. And it's not a coincidence that the moment the agent, if she were choosing her own information, would stop, the principal can't do anything at that point. There's nothing the principal can offer the agent apart from information. And if the agent doesn't want the information, she's going to stop using the app.
Sorry, I don't think I got that part. So the dashed line is where the user would stop, right? That would be their decision threshold.
Yeah, so the user's posteriors are roughly like 0.3 and 0.75.
And so the solid lines tell us what the principal is offering beyond that.
Yeah, the principal is going to get them not to be here and here as posteriors, but here and here.
Spend more time on the platform that you want to.
Yeah. And so dynamically, what does that look like? Well, the Q0 and 1 minus Q0, remember Q0 is your prior. 1 minus Q0 is sort of another spot where you're equally uncertain. Everything here is symmetric around half. This band is the band of suspensive beliefs between Q0 and 1 minus Q0. So you can have your stochastic process bouncing around in this band for a long time, but eventually you're going to jump to one of the principal's priors. You will never spend any time in this region, and you will never spend any time in this region. You will always stay in this band or jump to the outside priors. So those are sample paths of an optimal policy.
So I'm trying to understand it. So I guess the cost on the information is always X ante for a given period. Because like, it seems to be like when I jumped, I learn a lot of information in a short time, but in expectation, I don't.
When you jump here, you learn, yeah, exactly. It's always X ante for an instant. So these jumps are unlikely.
And so that's how the information per time constraint is satisfied.
Exactly.
So perhaps it's too early to think about that, but how would this play out in practice now? The idea is that the principal is sort of drip feeding information to me increasingly just enough to keep me engaged.
The way I interpret this is actually that they're showing you content all the time, but whether that content is what you want has a low probability. And then when they find something that you do want, you get a huge amount.
But how do they promise to me that I will later, get that strong signal?
Well, as we've discussed, actually, let's ask that. That's the commitment question, right? Is it credible that they will eventually give you something that you want? So if you want to implement one of the solutions where you go strictly in the middle here, where you raise the value of information, there's a commitment problem. Because the moment the user values the information more than when they started, the principal is tempted to re-optimize and extract that surplus. Because remember, the principal has full surplus extraction. If the user's value is positive, the principal has left something on the table. They could re-optimize and get it. But if you only bounce between these 2 points until you reach one of these points, then the value of information never goes up. And so what's going on here is that VR strictly positive requires commitment. But VR equals 0 and staying there does not require it. And so the only paths that are credible are the ones where you stay exactly where you started as the user in terms of your outside option. And so what this means is sort of interesting. Commitment matters when you think about the set of policies that are implementable by the principal, but it does not matter for the value the principal can achieve. So the principal can always achieve the same value with or without commitment, but the set of policies that it can use to do that is narrower if it doesn't have commitment. So here's some examples. This is, again, kind of the same set. So in this one, remember, everything is on a line and the prior was right in the middle. You can't move the belief. The only credible belief is exactly where you started, which is the prior.
For your geometry, how does the rectangle fit in the tetrahedron?
So this blue plane is like showing you the normal plane to the line segment on which your beliefs travel inside the tetrahedron.
It doesn't go to the boundaries of the tetrahedron.
On this one, though, there's something more interesting going on, which is, remember that the agent doesn't care about moving in this up-down direction. They only want to move in the left-right direction. So that means that there are actually a bunch of beliefs that you can travel on that are, even if you have no commitment. And it's those funky curves. So it would take a kind of weird stochastic process to stay on one of those curves. Like it certainly couldn't be a diffusion process, but in principle, there's space there. And what that's showing you is that it's basically an indifference curve of the agent, because the agent is indifferent and learning in that direction. All right, we have some extensions I'll tell you about. Here we've assumed that the principal controls the user's beliefs. The user, of course, always has the right to ignore the information that the principal sends. But they will never do that in equity. The principal is sending something useful with some probability. The user wants to pay attention to it. Now, they're not doing better than not paying attention to it, but they're not doing worse either. So actually allowing the user to selectively attend to the content changes nothing at all. None of you asked about this, but the opportunity cost of time rises the more time you spend on the platform. This is probably something you can confirm with your own life, right? The 5 minutes on your phone, you haven't really, blown off all your other obligations. 5 hours, suddenly problems. It's very hard for us to solve the increasing case. If we make just like a ton of assumptions, we can get kind of the same results. But I don't want to oversell it. One thing which I think is super interesting is, remember the logic here is that you have to stay in that set where VR is bigger than 0. And then you have to jump to outside. It turns out that if you require that beliefs be continuous, and you go to the 2-state example, then actually the user gets all the surplus. You need the jumps for the principal to get the surplus. And their intuition is that once you get to the point where the user will stop, the principal can't do anything. The principal needs the beliefs to jump over that point to get you to learn more than you otherwise would. So I thought that was sort of an interesting feature.
But in your x1 times x2 case, you can travel around.
Yes, exactly. And that's what this is ruling out. Yeah, exactly. I could diffuse in the wrong dimension in that case. Yeah. All right. So kind of to conclude, we think the content will be designed basically to send you down rabbit holes. And it's sort of a stochastic rabbit hole. If they try something, if that doesn't work, they'll try something else. There will be no consumer surplus. People will spend a long time on the platform, but not benefit in terms of their welfare. Now, they will make better decisions because they will acquire more information, but that will be offset by the cost of the time that they spent. They will either receive decisive signals that help them to stop quickly, or signals that leave them even more confused and further raise the value of the platform. And that's kind of how the platform strings them along. So that's our sort of theory. Obviously, there's like no data here. But we think that this kind of resonates with how at least some of these platforms work in the real world. And you know, I don't want to say the model generates testable predictions. That's a wild overclaim. But I think it at least speaks to some of the things that we see from the basic economics at play, which is that the platform wants to engage you, but doesn't really care what you do with the information.
So from, again, I guess trying to tie it back to like the bigger picture normative and regulation questions, whether what you have here is really a conflict of interest between platform and user. And if the platform decides you have in some sense too much time spent on the platform, I'd say we could care about doing something about it as a way of redistributing welfare to the user.
Yes, so I will say,
And there's no inefficiency here in this sense. There's no like Pareto suboptimality, right?
no, there is. So I was forced by the referees to take this out of the paper, but since none of them are here, I'm going to say it anyway. The way to solve this problem is have the user pay for the information with their money, not with their time. A platform that is paid by money has none of these problems. The problem comes because the platform gets paid in proportion to how much you use it, not paid upfront by the user. So my claim is that the Bloombergs and FTs and New York Times of the world, the reason that they provide you better stuff than the ad-supported media that's out there is that you pay them for the information and they don't have an incentive to waste your time. So in my view, that there isn't an efficiency here. If you allowed transfers, this would not happen. It happens because the user pays with time and not money.
And your intuition from where the inefficiencies come from.
Yeah, I mean, it's just the standard like lack of a price, right? Like clearly we could get better welfare in the following sense. User still gets 0. User pays money to the platform. Platform implements user's first best. Right? That's a more valuable signal to the user. The user would pay more than they would pay for this signal. So the platform must be getting more money. The user is still indifferent. Clear Pareto improvement. It's like an incomplete markets thing, right?
I think it's super elegant model. Can you try and tell?
Now I know you were.
Sorry. Exactly. Can you try and help me map it to reality a little better though? And so I think the main
Maybe you
thing
were.
the main thing that I'm a little confused about is that in the model, the result sort of seems to hinge on the user understanding that something good is about to happen, right? And
Or it might happen.
might happen. But so the platform can send them down a rabbit hole by promising them that there's going to be a gold nugget down there, and the user only leaves once they found this gold nugget, right? In a way, is that a correct
That's right.
intuition? Okay, which we can argue about whether or not that happens, right? But it's what I find interesting is that it's probably the only way to keep a rational user engaged.
That's right. Like, I mean, obviously, for something like YouTube, people watch the videos because they like the experience. Like, it's not clear that this has anything to say about that. I mean, I think there's some related aspects, but it's not a natural fit. I mean, that's why we did kind of the Facebook marketplace idea,
That makes sense.
is that we felt like it was a better example.
Yeah.
If a story about like you have to pay the New York Times whatever to read it, and that's the solution to the problem, then the implication would be that people spend less time reading the New York Times relative to its other source.
Yeah, I think it's a more efficient conveyor of information that,
But it's not just more efficient, people actually spend less time on there relative to it.
I think that's right.
That's right.
Yeah, I mean, I don't just find the articles that you want, right? Like I go to Wirecutter for product recommendations. It's less time than if I Google.
Sure.
Right.
So Wirecutter is not the New York Times.
Yeah, well, Wirecutter is a sub-brand.
Sure, but it's different.
Yeah. Well, and that's what I was saying. Like maybe this is really only specifically about decision-oriented things. I mean, I said this yesterday. I think people read the New York Times politics section mostly for entertainment. It's like a perverse form of entertainment that makes them unhappy, but it's not for them making any decisions. Right. Oh, and then I should say, that makes it sound like paying for the news is the solution to all the problems. But I think the reason that you want to not make people pay for the news is network effects. Like the reason that Facebook is much larger than the New York Times is that by getting people to sign up for Facebook, it raises the value of Facebook to other people and gets more people to sign up, right? And so in that kind of a setting, you don't want to charge people up front. So
From the platform's perspective.
yes, yeah, from the platform's perspective. So once you introduce that trade-off, I'm not clear what the social option is, but I think that's kind of the right thing to think about here.
Do you have an intuition about what happens when you introduce like the more behavioral system one type, whatever clickbait that I'm exposed, unhappy that I
So I think of this opportunity cost of time increasing as being isomorphic to I have a constant opportunity cost of time and a diminishing utility from the platform. So maybe the first video I like, and actually I have a positive cost of time, right? Because I'm benefiting. But then on the 10th video, my happiness has gone down. And now I'm just kind of, in a rut or something. So that's how I think about this one, but I can't really solve it very easily and I can't say much about it. So I would love to be able to.
But that's still not behavioral in the sense that I have like I do something different from my like well-considered interests.
Well, nothing about this says that this opportunity cost of time needs to be sort of let's say the value that you get from the video needs to be the rationally considered one, right? Like behavior.
You want to give a valid interpretation afterwards.
Behavior is sometimes distinguished between decision utility and welfare utility, and this is a decision utility object, right? So I make no judgment about whether it's good for people. Well, thank you. Yep.